Okay, this is going to change the topic a little bit, and we're going to talk about percent composition and a way that chemists can figure out chemical formula of something by figuring out the percent composition. So we're going to go one way and then the other way. So let's first start with a definition. What is the percent composition definition? The percent composition of a compound is the mass percent of each element in the compound. So mass percent then is the mass of the part divided by the 100 grams of the total. So what is the, in other words, parts of A per 100 parts of the total. So in other words, the mass percent is the mass of A divided by the mass of the whole thing times 100%. So just like any percent composition, the part divided by the whole times 100. And I could do that if, like, let's say my compound is AB. We don't know if it's, X, or we don't know the numbers, but there's A and B. Then I could find the mass of B, which is, or the mass percent of B will be the mass of B divided by the total. So let's look at an example of that. An easy example. So let's calculate the percent composition of butane. So in other words, we want to know what's the mass percent of carbon and what's the mass percent of hydrogen. What I want to point out to you, and this is a really important, if you can get this idea right from the start, I think that a lot of these problems will be much easier for you. When I see a formula like this, I know it's my ratio, right? So if I have one molecule of C4H10, that means I have 4 carbons and 10 hydrogen. If I think about this, again, I can also think, and let's go with like the bunny rabbits. If I have a dozen of these, I have 4 dozen carbon and 10 dozen hydrogen, right? So this is, and I could also say if I have a mole of butane, I have 4 moles of carbon and 10 moles of hydrogen. So when I see a formula like this, I can think of it as a mole to mole ratio. If I have a mole of this, I have 4 moles of carbon and 10. So this has nothing to do with weights. It has everything to do with counting how many of each I have. And when we talk about moles, again, that's just a counting number. It's just a definition. Like I said, a dozen, a mole, same idea. But now in this case, we want the mass percentage. So we have to know how much each of these weigh. So we want to know the mass of carbon. Well, there's 4 carbon atoms, and each carbon atom is 12 grams per mole. So that means the 4 carbon atoms weigh 48 grams. Let's do the same thing for hydrogen. Okay, there are 10 hydrogen atoms, and each of them are 1 gram, 1.01 grams. So 10.1 grams. So again, this is going to be very different. If we have counting numbers, it looks like we have a whole lot more hydrogen than carbon, right? Because there's 10 hydrogen and 4 carbon. But remember, every element has a different mass, and so it's not going to be the same for our mass ratio. So 4 carbons equal 48, 10 hydrogen equals 10.1. So what's the total mass of this molecule? 58.1 grams. 1 mole equals 58.1 grams. So that's good. Now we can see our mass percent is going to be very different than 4 to 10. So our mass percent of carbon will be the mass of carbon, 48, divided by the total mass, 58.1. That gives us 82.6% by mass of carbon. Let's do hydrogen. If there's only 2 things, they should add up to 100%. So you could either do the hydrogen like this, 10.1 divided by 58.1 gives me 17.4%, or I could also subtract 100 minus 82.6 should give me 17. Now, it may not always add up to exactly 100. It may be off by a decimal, and that has to do with rounding and significant figures and things like that. But anyway, here's our mass. So clearly, remember again, a formula like this is kind of counting. There's 4 carbons and there's 10 hydrogen. But in terms of mass, we know that carbon weighs a whole lot more than hydrogen. So overall, in the whole molecule, the biggest mass, 82.6% of the whole thing, is the carbon, and only 17% is the hydrogen. So just two different, and this is actually this is the problem we come up with in chemistry from the very start, is that every element has a different weight from each other. So we can have our counting numbers and then we have our mass numbers, and they're different, and we have to keep converting back and forth all the time because everything rearranges itself. And so anyway, all right, so that's the mass percent. Now, that's very interesting, but actually not very useful. So what we're going to do is kind of work the other way around. So like if I worked in a laboratory, I might work in a laboratory where there's an unknown compound. We know what elements are in it, but that's all we know. And somehow you can do some experiment where you can figure out the mass percent of each element. So if I gave you that, can you figure out what is the formula? So again, notice in that last slide, we took the mole ratio and we converted it to a mass ratio. So now we're going to do the opposite. If we're given a percentage, we're going to take the mass ratio and convert it to a mole ratio. So just keep that in mind. We're just going back and forth. So this is an example, more likely something you'll encounter. If I have a percent composition, I can get the empirical formula of the compound in question. Remember, the empirical formula is the lowest ratio. So we'll come back and talk about that in a minute, but it's the lowest ratio of the moles, the formula. So again, empirical formula is the substance written with the smallest whole number subscripts. Remember, we talked about this in the previous chapter. If C6H6 is the molecular formula, the empirical formula is CH. N2H4 being the molecular formula, the empirical formula is NH2. Now, if the molecular formula is already in its lowest terms, then the empirical formula and the molecular formula are the same. So like, for example, CH4, you can't reduce that down anymore, so the empirical formula. So it doesn't always have to be, but just so you have that in mind. All right, so let's kind of do an example. So, okay, so let's say I analyzed a compound. This time I don't have percentages, but I just have masses. And I say, all right, I've taken a sample and I've broken it down into its components, and out of the total mass, 13.5 grams is calcium, 10.8 grams is oxygen, and 0.675 grams is hydrogen. They don't quite add, well, sig figs are kind of off, but they all have 3 sig figs. But if you tried adding them together, you only want to be to the ones place. So it's approximately 0.7, but we'll keep those numbers. Okay, so the question is, so remember, these are masses. But what we want to find is, what is the formula? What is the empirical formula for this compound? So in other words, we're looking for those counting numbers, the mole ratio. So remember, this is the mass ratio, but we're looking for the mole ratio. So in other words, we're looking for this. We want to know how many calcium does this represent compared to how many oxygen compared to how many hydrogen. So that's why I used X, Y, and Z. These are unknowns. We don't know what those values are yet. It's going to be some whole number ratio to find the formula. All right, so remember again, if we've got grams, remember that a formula always represents moles. So what we need to do is we need to convert from grams to moles for each of these. If we take the grams and convert it to find out how many moles that is, how many moles is this, how many moles is this, then we have our mole ratio. So let's do that. So if I take 13.5 grams of carbon, 1 mole of carbon is 40.1 grams. Again, that's from the periodic table. That gives me 0.337 moles. Let's do the same thing for oxygen. 10.8 divided by 16.0 gives me 0.675 moles. I'm starting to see a little pattern here, but let's do the same thing for hydrogen. 0.675 grams of hydrogen divided by 1.01 gives me 0.668 moles of hydrogen. Okay, so that's good. Now we can sort of see the mole ratio. And hopefully you can already see that this is about twice of the 0.337. That's about twice as much. That's about twice. These are really close in size, and this is about twice of that. But let's go ahead and lay it out. If you can't see that, that's fine. We're going to do something to be able to see it better. So really what this means is the mole ratio is this: Ca 0.337, O 0.675, H 0.668. Okay, well, we know that formulas are not written with decimals. We want whole numbers. I think you can almost already see the ratio, but if you can't see the ratio, the best way to do that is to take each number and divide it by the smallest one. So in this case, 0.337 divided by itself, because it's the smallest one, gives me a ratio of 1. 0.675 divided by 0.337, it's going to be really, really close to 2. And 0.668 divided by 0.337, same thing, it's going to be really close to 2. It may not be exactly 2, but it'll round really close to 2. So now we can see, I mean, all these numbers are not going to be perfect, but they should round to pretty much whole numbers. They might round to like half numbers, or third or half will sometimes happen. I think I'll show you an example of that in a second, but anyway, they should be whole numbers. If they don't, you've probably done something wrong. So most of these problems are made this way. Anyway, now I can see my ratio. That's really easy. Now I know I have 1 Ca for every 2 O's and 2 H's. So even though the mass ratio is very different, here's my mole ratio. This is actually the compound calcium hydroxide, which is that, but you wouldn't necessarily know that, and this would be a perfectly fine answer right here. All right, so like I said, be really careful. Don't round too much. In this case, let me see. So like 0.675 divided by 0.337 gives me 2.00. So 2.003. So to three significant figures, it's 2. If I take 0.668 divided by 0.337, I get 1.98. So that's really close to 2. So I can round that up to 2. So these are all rounded to whole numbers. The next example, you'll see you don't want to round too much because it could mess you up. So let's look at another example. All right, and two things I want to show you in this example. So benzoic acid is a white crystalline powder used as a food preservative. If you read some labels, you might see benzoic acid. The compound contains 68.8% carbon, 5.0% carbon. I guess these all are to 1 decimal place. So 5.0% hydrogen and 26.2% oxygen by mass. So you can see they should add up to 100%. What is the empirical formula for benzoic acid? So again, what are we looking for? Empirical formula. Remember, formulas are mole ratios. These are mass ratios. So that's what we're looking for. We want to know how many carbons compared to how many hydrogens compared to how many oxygens. So just like what we did before, we had to convert from mass to moles using the molecular weight. So that's our first step. Now, the first thing you might say is, wait a second, there's no masses here. I don't know, how do I convert percentages? Well, just remember what a percent is. There's 100, you've got 100%. So let's just assume we have 100 grams. It doesn't matter how much you have. You could assume you have 1 gram, or you could assume you have 5 grams, or you could assume you have any grams and just figure out how much that means using the percents. But the easiest thing to do when you have percents is to assume you have 100 grams. If I have 100 grams, that means I have 68.8 grams of carbon, I have 5.0 grams of hydrogen, and I have 26.2 grams of oxygen. So my percentages can just be converted to a gram if I just make that assumption. So now I know the gram ratio, mostly carbon, tiny bit hydrogen, a little bit of oxygen. But remember this, what are these ratios? These are mole comparisons. So the first thing I have to do is convert each of these to moles. So this is just telling you to assume 100 grams. Again, if you want to assume 1 gram, then you could divide everything by 100 and you'd have 0.688, 0.005. That would be fine too. You can use anything. Just go with the easiest, which is this. All right, so the first thing we're going to do is convert masses to moles. 68.8 grams of carbon divided by the atomic weight of carbon gives me 5.73 moles of carbon. 5 grams of hydrogen gives me 5 moles of hydrogen. If I had 1.01, see, that's where in that last problem it was 1.01 or 1.0. It really is making just a slight difference. So it's not critical if we divide it by 1.01, but all of these are, we'd have 4.95. So close enough. They all should round pretty close to whole numbers. Okay, and then 26.2 grams of oxygen divided by 16 gives me 1.64. So here's what I'm saying. Don't just automatically round here, because if you did that, you might say, well, there's 6 carbons, 5 hydrogen, and 2 oxygen, but they're not close enough to round. So just like we did before, the best way to see the ratio is to divide by the smallest one. So the smallest one is 1.64, so let's do that. All right, so here we have our 5.73 moles of carbon divided by 1.64 gives me 3.5. 5 moles of hydrogen divided by the smallest 1.64 gives me 3.0. And then oxygen gives me 1.0. Again, don't round. It would be very tempting to say 1 to 3 to 4, but that's not right. So notice, since that's really, really close to a half, you want to make whole numbers out of all of these. So what I'm going to do is multiply everything by 2 to get rid of my decimal here. So if I multiply this by 2, I get 7. If I multiply that by 2, I get 6. And if I multiply that by 2, I get 2. So here's my ratio. C7H6O2. And you can see where mistakes might have been made if I did too much rounding. So you want to really wait to the end. Sometimes also something might come out really close to 0.333, and then in which case you want to multiply everything by 3 to clear that third fraction out. So anyway, so the empirical formula here for benzoic acid is C7H6O2. This is just a little bit of a little picture showing you. So if you know the mass of the atoms, divide by the molar mass or the atomic mass to find the moles of the atoms. Like let's say you have, this is telling you that you have a sample that's A. Let's do, they use X, so that's not good. So let's use S. We want to know how many A's there are, and we want to know how many X's there are in this formula. So if we take the mass of A, divide by the atomic weight of A, we get the moles of A. If we have the mass of X, we divide by the molar mass to get the moles of X. So now we have the mole ratio. The best way to find the whole number ratio is to divide by the lowest number. That gives us our mole of A, our mole ratio of A to X. If it's not whole numbers, you might have to multiply by a factor to get them to whole numbers. So convert this ratio to the lowest whole numbers, and that gives you your empirical formula. And like I said, if you're given percentages rather than mass over here, convert the percentages to mass, just assuming you have 100 grams, and then you can make that. So this might be a little helpful mnemonic to remind you what to do. I have a lot of students who forget this step. they'll say, oh yeah, I remember dividing by the lowest. So they'll start here and divide by the lowest and forget that you have to convert to moles before you can do anything else. So this mnemonic might help you. All right, now one more step sometimes is involved. So remember what we said is right now the only thing you can get with this process is the empirical formula. Remember, it's the smallest whole number ratio. And remember we said that the molecular formula then is some multiple of the empirical formula. So sometimes you'll be given, you go through the whole problem and you get your empirical formula, and then it will ask you a last question. It'll say, well, here's the molecular weight of the unknown compound. What's its molecular formula? So let's see how we would go about doing that. I think our benzoic acid, I think on that last, we can look at this, but the last example, our benzoic acid, the empirical formula was actually the molecular formula. But let's look at another example. So let's say we did that whole process for some unknown, and we came up with the empirical formula CH2O. So that's our lowest ratio, but we're not sure if that's the molecule or not. But then I say, what's the molecular formula? This is the empirical formula. What is the molecular formula if its molecular weight is 60 grams per mole? Well, remember that our molecular formula is just a multiple of our empirical formula, right? So the answer could be CH2O, could be all ones. It could be C2H4O2. It could be C3H6O3. It could be C4H8O4. It could be any of those multiples. So how do we know which multiple it is? Well, the easiest way is to say, all right, we have the mass of the whole thing. Let's find the mass of this. So 1 carbon is 12. 2 hydrogen is 2. I'm sorry, 1. Let's erase that. Each hydrogen is 1, so 12 plus 2 plus 16 gives me 30. Now you can see this weighs 30. The actual molecules weigh 60. Well, you can already see it's 2 times as much. But if you can't see that, sometimes you don't know multiples very well. Hopefully you can see that's twice as much as that. But if you don't know, you can actually take the bigger one divided by the smaller one. So there's my 30 grams per mole. Take the bigger one divided by the empirical. Take the molecule divided by the empirical. 60 divided by 30 is 2. So we know our chemical formula, our molecular formula, is twice that of our empirical formula, so just multiply everything by 2. Don't leave a 2 out front, but you want to actually multiply by 2. So there's 2 C's, 4 H's, 2 O's. So that's just a real simple ending. I believe the benzoic acid was C7H6O2, so it was the empirical formula and it was also the molecular formula.